There's a technology poised to change the game for electric cars in a way few are yet to see. And it's not arriving from the distant future. It's knocking on the door now. In the second half of 2026, the aluminum-ion battery will begin to move from the drawing board to reality, bringing with it a promise that electric car owners have waited years for, charging the car in less time than it takes to heat a meal in the microwave. This is no exaggeration. The numbers emerging from laboratories and engineering tests point to a reduction of up to 70% in charging time compared to what exists today. And that alone would be enough to turn the industry upside down. But the story doesn't end there, because along with the charging speed comes something drivers desire as much as the extra range this battery also delivers. Aluminum-ion batteries aren't just faster. They carry an energy density that allows them to store more energy in the same physical space that lithium batteries occupy today, which in practice means a car can travel more km on the same charge without needing a larger or heavier battery pack. This changes the entire design calculation for an electric vehicle, because engineers no longer need to increase battery size to deliver more range, and can now work with margins that simply didn't exist before. The result is a lighter, more efficient car with a battery lifespan that tends to be significantly longer than the current market standard. For the average driver, this translates to fewer stops, less worry, and more confidence in everyday life. It is precisely in this context that the Model 2 truly begins to make sense. Tesla's cheapest car, designed to cost close to $25,000, has always faced a silent obstacle: the cost of the battery. With conventional lithium-ion, achieving that price without compromising quality or range was almost an impossible equation to solve. Aluminum changes this equation because the material itself is more abundant, cheaper to process, and doesn't depend on the same scarce and politically sensitive supply chains that lithium and cobalt require. This means that Tesla can look at a large-scale production line for the Model 2 without having to pray that the price of raw materials doesn't explode along the way and make everything unfeasible. When news of a revolutionary battery arrives, the first question that inevitably comes to mind for anyone who already owns a Tesla is, can this technology be installed in my car? It's a fair question. After all, nobody wants to be left behind as technology advances, especially those who have already invested a considerable amount in an electric vehicle. The answer exists, but it comes with a series of details that make all the difference between a successful upgrade and an expensive problem that nobody wants to face. Replacing a Tesla's battery with an aluminum-ion pack isn't like changing a tire or updating software on your phone. It's a process that requires compatibility on multiple levels simultaneously, and ignoring any one of them is the shortest path to a priceless headache. The first point that needs to be aligned is the vehicle's physical structure, the so-called mounting points. Older Teslas were designed with specific fittings and supports for the battery packs that existed at the time, and these fittings don't always match the shape of the new aluminum-ion modules. Furthermore, the cooling system is another critical element that is often overlooked in retrofit discussions. Aluminum batteries operate under different thermal conditions than conventional lithium batteries, especially during fast charging, and an undersized or incompatible cooling system can compromise both the performance and durability of the new pack. This isn't a minor detail. It's a basic requirement for the replacement to work as intended. There is also a third layer of complexity that is completely invisible to an outsider: the battery management software, known as BMS, short for Battery Management System. This system is the brain that controls how the battery charges, discharges, regulates temperature, and communicates with the rest of the vehicle. The problem is that each battery generation speaks a different language, and the BMS of a Tesla manufactured a few years ago simply wasn't programmed to understand the voltage and response patterns of aluminum-ion batteries. Without a thorough upgrade of this system, either through additional hardware or compatible reprogramming, the car cannot use the new battery pack safely or efficiently, regardless of how good the installed battery is. Given that retrofitting isn't a universal solution, the question remains: what's the right approach for each Tesla owner? The answer depends directly on the vehicle's year, and this division isn't arbitrary. It reflects real engineering differences that determine how much work, money, and risk are involved in each case. There's a kind of unofficial map that divides Teslas into three distinct groups. And knowing which group your car falls into is the first step before any conversation with a repair shop or any budget research. Each group has its own compatibility profile, its own technical requirements, and its own limitations, and treating them all the same is a mistake that can be costly. Vehicles manufactured from 2021 onwards come closest to a truly seamless experience. In this generation, the standardization of mounting points and cooling systems is already well established, and the BMS is modern enough to receive necessary software updates without the need for complex additional hardware. In practice, a qualified technician can remove the old package, fit the compatible aluminum-ion module, and seal the system with far less structural intervention than any previous generation would have required. It's not a fully automated process. It still requires attention and validation, but it's the closest scenario to what the industry calls a drop-in. That is a replacement that respects the vehicle's original architecture without forcing adaptations not foreseen in the design. The second group, comprised of Teslas manufactured between 2018 and 2020, still has a viable path but requires a different approach from the start. During that period, standardization was still underway, and some specifications varied between manufacturers and models, meaning that perfect alignment between the new module and the existing structure doesn't always happen naturally. The most common technical solution involves installing an auxiliary BMS bridge, an intermediate hardware component that translates communication between the aluminum battery pack and the car's original system. Furthermore, charge and discharge limits need to be conservatively configured, which in practice means the vehicle won't utilize the new battery's full potential, but will operate stably, predictably, and within safety parameters that protect both the car and the warranty. After understanding which group the vehicle belongs to and whether retrofitting makes sense from a technical standpoint, the next question that inevitably arises is about money. How much does it cost? How long does it take? And what exactly is included in that price? These are legitimate questions, and the answers need to be addressed honestly because the retrofit market is still new enough that vague estimates and exaggerated promises circulate easily. Technical data available up to the second half of 2026 indicates that a complete retrofit for an approximately 60 kW aluminum-ion battery pack already installed by a certified workshop starts at around $5,000. This number, however, is a starting point, not a ceiling, and understanding what can drive that value up is as important as knowing the price itself. The final cost of a retrofit is influenced by a number of variables that change from case to case. Geographic location directly affects the price of labor, which can vary significantly between regions and countries. The availability of parts in the local market also weighs in because imported modules with complex logistics are more expensive than components available from established regional distributors. If the vehicle belongs to the second group models from 2018 to 2020, the cost of the auxiliary BMS bridge is factored in and can add a significant portion to the total budget. Local taxes, certification fees, and any adjustments to the cooling system are other items that appear depending on the state or country where the service is performed, and ignoring them when planning the budget is a classic mistake that turns an encouraging estimate into an unpleasant surprise. Vehicle downtime is another factor that deserves attention because it directly impacts the routine of those who depend on their car daily. An experienced and well-equipped workshop can complete the process within 1 to 3 days, provided the scope of work is clear from the start and no surprises arise during disassembly. The problem is that surprises do happen. A corroded mounting point, a damaged cooling connector, or a software incompatibility that only appears on the diagnostic bench are examples of situations that extend the time frame without prior notice. Therefore, any responsible planning should include an additional time margin and avoid scheduling the retrofit during periods where the vehicle's absence for a few more days would be a serious problem. Solving the battery problem is an essential part of the equation, but there's a layer beneath all of that that rarely appears in headlines about electric technology. It's pointless to have a car capable of charging in minutes if the surrounding infrastructure can't deliver that energy stably, affordably, and efficiently. It's like having a car capable of reaching 300 km/h in a city where the speed limit is 60 and the traffic lights are broken. The potential exists, but the environment doesn't allow it to manifest. And that's precisely the silent challenge that accompanies the arrival of aluminum-ion technology in the second half of 2026, a technology that demands a high-quality infrastructure to ensure its promises move from theory to reality in the driver's experience. The first element of this infrastructure is energy storage at the charging stations themselves. When many vehicles connect at the same time, especially during peak hours between late afternoon and early evening, energy demand rises abruptly and puts pressure on the local power grid. The solution being implemented in the most advanced charging hubs is the use of megapacks, large stationary storage systems that absorb energy during periods of low demand and release it in a controlled manner when traffic at the stations increases. In practice, this means that a driver arriving to charge at 6:00 p.m. at peak grid consumption can still get a fast and stable charging session because the megapack is silently discharging behind the scenes, balancing the load without the grid needing to deliver everything at once. Dynamic pricing, known in the industry as too short for time of use, is another game-changer for those who charge at home. This billing model divides the day into different price ranges, and the cheapest range usually occurs between 2 and 5 a.m. when overall grid consumption is at its lowest. During this interval, energy can cost between 40% and 60% less than during peak hours, and a vehicle programmed to automatically start charging during this window takes advantage of this difference without the driver having to do anything other than plug in the cable when arriving home. It's not a matter of giving up convenience, It's a matter of using already available technology to consistently and automatically reduce monthly costs. While charging infrastructure evolves, another technology is gaining traction in conversations about the future of electric vehicles, and it completely reverses the logic of what is understood by a grid-connected car. Instead of just receiving energy, the vehicle also starts supplying it. This concept is V2G, short for vehicle to grid, and it represents an important shift in perspective. The car ceases to be just a consumer of electricity and begins to function as a mobile battery that can interact bidirectionally with the electrical grid and the driver's own home. The idea is seductive, especially in a world where energy tariffs are rising and blackouts are occurring more frequently in various regions of the planet. In practice, V2G works as follows. When the electrical grid is overloaded and energy prices rise, the car can return some kilowatt hours stored in its battery to the grid, receiving a financial credit in return. Similarly, during a power outage, the vehicle can power essential household appliances such as the refrigerator, lighting, and router, functioning as a silent generator parked in the garage. This second use, called V2 or vehicle to home, is where V2G finds its most concrete and immediate application for the average driver, because it transforms an asset that is already idle for most of the day into an active resource for domestic energy resilience. The problem begins when the analysis goes beyond the emergency scenario and enters the territory of daily use as a source of income. The logic seems simple at first glance. Sell expensive energy during peak hours and buy cheap energy during the early morning hours. But the real numbers of this operation rarely deliver the return that theory suggests. Each charge and discharge cycle of the battery consumes a fraction of its total lifespan, and this wear and tear has a cost that needs to be deducted from any profitability calculation. When considering the real efficiency of the round-trip energy cycle, which takes into account losses in bidirectional conversion, the value received per kilowatt-hour return to the grid, and the accumulated degradation of the battery, the remaining net margin is usually too small to justify the intensive and daily use of this functionality. All this talk about faster batteries, smart retrofits, and cars powering homes begins and ends in a place most people never visit: the factory floor. It's there that the difference between a revolutionary technology and a technology that truly changes the world is decided. Not in research labs, not in investor presentations, and not in internet headlines. Aluminum-ion technology has already demonstrated its capabilities in a controlled environment, and the numbers are impressive enough to justify all the attention this chemistry has been receiving. But demonstrating performance in a lab and producing millions of units per year consistently at controlled cost and with zero compromise on quality are two completely different challenges. And the automotive industry has a long history of technologies that promised much and delivered little because they failed to cross that chasm. Industrial scale is unforgiving to innovations that aren't prepared for it. When a factory needs to produce tens of thousands of battery modules per month, every millimeter of variation in the manufacturing process, every fluctuation in material purity, and every bottleneck in the assembly line becomes a problem that multiplies by thousands of units before anyone can identify and correct the source. With aluminum ion, this challenge is amplified because the technology is still in its early years of real industrial production, meaning that learning curves are still being charted, suppliers are still being qualified, and processes are still being refined. Each of these steps takes time, and time is precisely what Tesla's competitors aren't wasting. The supply chain is the second node in this race. Aluminum itself is abundant and well-distributed geographically, which solves one of lithium's biggest problems: its dependence on deposits concentrated in a few countries and logistical routes vulnerable to geopolitical tensions. But the components that transform raw aluminum into a high-performance battery cell are neither simple to produce nor to scale up. The specific electrolytes, separators, layer deposition processes, and manufacturing equipment require specialized suppliers who are still developing their own production capacity in parallel. An interruption at any point in this chain, whether due to capacity issues, regulatory problems, or logistical setbacks, has the power to delay the entire downstream production line and compromise publicly announced schedules with precise dates. What's at stake in this race goes beyond Tesla and the Model 2. Automakers from different parts of the world are watching the advancement of aluminum-ion technology closely because they know that the first company to master the large-scale production of this chemical will establish a competitive advantage that will be difficult to reverse in the short term. Lower battery costs mean higher margins or lower final prices, and in both cases, the effect on market share is immediate and powerful. The race is not just technological, it's industrial, logistical, and financial all at once. And winning in the lab without winning in the factory is useless in a market driven by the ability to deliver products to the customer in volume and on time.